Graphs everywhere. No, but in all seriousness, in this section, we're going to look at some more properties of functions. And for the majority of it, it is going to be based on functions graphs, but there will be some algebra involved, particularly in the section of notes that will, the part of the notes that we'll do today from this section. So I'm going to dive right into it and finish class off with this discussion on a certain class of functions, and that class would be even and odd functions. And we have actually done some work with these. I just didn't tell you that we were when we were working with symmetries in chapter 2. So this actually closes the loop on all that. That's the reason why we were working with symmetries in chapter 2, is because some of that work applies directly to these two types of functions. Let's start with a function whose graph has y-axis symmetry, as you're seeing below. Okay, the axis of symmetry here is the y-axis, and the part to the right of it is a mirror image of the part to the left of it. Functions that have y-axis symmetry are known as even functions. Functions may have origin symmetry, which is what the second graph is displaying. Keep in mind what makes a function have origin symmetry. If we look at corresponding points, such as -1, -1, and 1, 1, is that if we were to draw a line segment connecting the corresponding points, you would always pass through the origin. Functions that have origin symmetry are known as odd functions. Now you might be wondering, why are we not looking at graphs that have x-axis symmetry? Well, that's pretty easy to explain. Here's a graph with x-axis symmetry. Think about the definition of a function, or how we were testing to see if the graph is the graph of a function. Would this graph that I just drew be the graph of a function? No, it's not a function. It does not pass the vertical line test. And that's why we actually don't look at graphs with x-axis symmetry. In most cases, they do not represent the graph of a function. So we leave those off, and we just worry about those graphs that have y-axis symmetry and origin symmetry. Now I'm going to give you kind of an analytic way of defining functions that are even and odd. But just in case anybody's wondering, are there functions that don't have either types of symmetry? The answer is yes. And those functions that don't have y-axis or origin symmetry, or in other words, functions that are not even and are not odd, we just call them neither functions. Now there's a way to make a connection between the corresponding points of these types of functions. An even function is going to satisfy this property. F of negative x is equal to f of x. Let's see why that is with a couple of corresponding points on our even graph. Let's look at -3, 3 and 3, 3. These are two corresponding points. Okay, if you were to fold the graph along the y-axis, they would line up. Now, based on function notation and how it relates to y-coordinates, it's true that f of -3 is equal to 3, because that's the y-coordinate when x is -3. If we look at the y-coordinate when x is +3, the y-coordinate is 3 as well. So since 3 is equal to 3, this actually shows that f of -3 is equal to f of +3. And so we get the same output when the inputs are opposite of each other. And that's exactly how we define an even function. F of negative x is equal to f of regular x. Okay? Now for an odd function, it works like this. F of negative x is equal to the opposite of f of x. And to see how that works, let's look at our corresponding points with the odd function graph. That y value of negative 1 is what f of negative 1 is equal to. And then this y value of positive 1 is what f of 1 is equal to. And notice how these y coordinates are opposites of each other, and so are the x coordinates. So the x coordinates and y coordinates are opposites of each other. So here's something that we could say about this. F of negative 1 is equal to the opposite of f of 1. Can you see how that makes sense? Like if we were to take the opposite of negative 1, we would get positive 1. Is that gelling with y'all? So in this case, opposite inputs create opposite outputs. Notationally, that means f of negative x is equal to the opposite of f of x. So I'm going to do my best to show you how we can determine if a graph has y-axis symmetry or origin symmetry by using some reflections. Now keep in mind, a graph that has y-axis symmetry is the graph of an even function. And a graph that has origin symmetry will be the graph of an odd function. So to test if a graph is the graph of an even function, and this is kind of the appropriate thing to do when your graph is provided, but maybe you don't have any ordered pairs listed out for you. Unlike part A, we can probably get a sense of what kind of function this is based on ordered pairs. But in the event that you don't have ordered pairs on your graph, you can do a reflection across the y-axis. And I'll show you how to do that as best as I can with some drawing. And if your graph matches up with the original version of the graph, then that can lead you to the conclusion that your function is even. Now, if you find that your function is not even, it might be odd, in which case you not only do a reflection across the y-axis, but you proceed to do a reflection across the x-axis afterwards. Okay, so there are two reflections involved. The first is the y-axis, the second is the x-axis. And once you've done the x-axis reflection, if that graph matches the original, then the graph is a graph of an odd function. Now, in some cases, you can go through all these reflections and it not match up with the original. And that's okay. It just means that it's a neither function. All right, so let's look at how we can test some graphs out to see if they're even, odd, or neither. In part A, we have this little squiggly graph here. And I'm going to show you how you can do a y-axis reflection to see if it's even. I'll make a little workspace for it. Y-axis. I'm going to draw out a coordinate plane as best as I can. And we're going to reflect our graph across the y-axis. And I like to do that in kind of like pieces. I'm going to look at the piece that's to the right of the y-axis from our original graph, this right here. And we're going to mirror that over to the left-hand side. And when you do so, you end up with the graph or that piece in quadrant 2 situated this way. And we're going to do a similar thing with the part of the graph that's to the left of the y-axis, namely this part. We're going to reflect it across the y-axis this way. And this would complete our y-axis reflected graph. Now, all things considered, all right, this isn't drawn 100% accurately. Do you think this would look any different than our original graph if it were 100% accurate? Correct. Yeah, so upon doing a y-axis reflection, we actually get the same graph, don't we? So this means that there's y-axis symmetry. And any function that has y-axis symmetry would be representative of an even function. Now, we won't bother to do the x-axis reflection because you can't have a function that's both even and odd. Just like with numbers, right? You can't have an odd number that's even, so on and so forth. So if you establish after your first reflection that your graph is even, you're done with the problem. All right, but if you do your y-axis reflection and it doesn't match up, you want to proceed to do your x-axis reflection. So let's see if that applies with our graph in part B. We'll do a y-axis reflection with this graph. Again, pardon my drawing. I'll start with the piece that's to the right of the y-axis. That's going to get mirrored across it. Oh, not sure what happened there. All right, I wanted to highlight the y-axis, so there we go. All right, so this piece to the right of the y-axis is going to get mirrored across it. And when you do so, this is what results. And then we'll do the piece that's to the left of the y-axis. And that would complete our y-axis reflected graph. Now, if this were drawn with 100% accuracy, would it match the original version of our graph? Definitely not. So this means our function is not even, which opens up the door for the possibility of it being odd, in which case we'll have to, well, actually I don't want to write origin. I want to write x-axis because these are titles for our reflections. Sine functions are always odd provided there's no horizontal or vertical shifting. So as long as there's only like a period change, then they would be odd. Yeah. By the way, math puns are the first sign of madness. Get it? Okay, so we're going to proceed to reflect our y-axis reflected graph across the x-axis. So with our second reflection, we're going to base it on the reflection that we just did. And I'll start with the piece that's to the right of the y-axis. We're going to flip this across the x-axis. Okay, and when you do so, that piece gets flipped upside down like that. And then we'll do the part that's to the left of the y-axis. We'll reflect that across the x-axis. to get something like that. Now again, human error here. It's not 100% accurate, but if it were, okay, so if this x-axis reflected graph were 100% accurate, would it match up with the original graph? For sure. So this matches the original. I'll say matches OG, meaning it has origin symmetry. And that implies that we have the graph of an odd function. All right, so we have just a couple more minutes left. I think that's probably enough time to give you a shot at this with part C. Okay, once we go over the answer, if you have any other questions, I'll be happy to answer them. Otherwise, I'll dismiss you and wish you guys all a great spring break next week. But take the next couple of minutes to see if you can determine whether the function's graph in part C is the graph of an even, odd, or neither function. Okay, then we'll go over it, and that'll be it for us for today. All right, I'm going to sketch my reflections out. Let me know if you have any questions along the way. Y-axis reflection does not indicate that this function is even. All right, this y-axis reflection doesn't match up with the original, so our function's not even. It might be odd, so we should verify whether or not it is. And what I'll do is take what we just reflected and swivel it across the x-axis. And when we do so, you end up getting something like that. Does this graph match up with the original? No. So what kind of function is this? Yep, it's a neither function. So no x-axis or origin symmetry. That implies neither.